Okay, so last bit on geometric optics, which is treating light as a ray, is to talk about refraction. And refraction, at the end of the day, is where rainbows come from. It's also why when you put something in water, it appears to like bend. It's all about refraction. So that's what we're going to try to cover here. After this, we'll cover all of physical optics, which I looked in the AP CED, and there's really not that much actually. So they don't want you to know about the Doppler effect, so we won't talk about that. It's kind of a shame because it's used in a lot of stuff. And instead, we'll just talk about what they wanted us to talk about. So, real quick, we got a little bit of time here. Does anybody know why rainbows happen?
The splitting of white light.
Okay. So why does that happen? Why does that happen when it rains?
Because of refraction.
Very, very good. But why does that make a rainbow?
The light.
I don't know. That's how much light is and it breaks it up into the different visible light colors.
So why does that happen?
Because God made that light. We have like because our eyes are shaped like this, and Earth is shaped like this.
No, but I love it. Okay, so here's the deal. You probably understand that rainbows happen because there's water in the air, and somehow the light gets split apart in the water droplets and you see a rainbow. But then there's all sorts of questions like, why does that actually happen? Why does that make an arc, right? Like, why is it not just like everything rainbow as like a big drape? Like, why is it a bow, right? Why does that happen? So that's what we're going to talk about, is like why all those things happen. And yes, the answer is refraction and resulting dispersion, which are the two topics we'll cover here. They're the last things we need to talk about with ray optics, or geometric optics. So, getting into it. We don't need all that. We don't need all that. Refraction. Why light bends when it changes mediums. This is all refraction is. Refraction is the idea that as light changes mediums, it's going to bend, and we call that phenomenon refraction. So, the simple answer is that the speed of light slows as it passes through a medium. Now, quick misconception alert. Remember, I told you guys the other day that the speed of light is always the same, right? But as it gets absorbed and re-emitted, it effectively slows down the light as it travels through materials. Okay, it's a minor, like, nitpicky point, but hopefully that'll keep you from having misconceptions later on in life. To just remember, the actual light itself always travels the same speed, but when it's absorbed and re-emitted, that takes a little time, which effectively makes it seem as if the light is traveling slower. So here's the deal. As the light changes mediums, that changing of speeds ends up making the light bend its pathway just a little bit. Okay? The reason for that is if you imagine a wave front, the wave front will hit the medium on one side first. And so that first edge will slow down first. And while it's doing that, it's kind of like the front will pivot around that slower point, which effectively ends up bending the light. Normally I have you guys go outside and like do a whole thing. Not important. Just know that when it changes mediums, media, that's the plural of mediums. When it changes media, it's going to bend depending on how the speed of light changes. Okay? From here on, I'll be shortening to just say the speed of light changes. I hope you understand what I mean when I say that, because it's the easiest way to communicate. So whether the light speeds up or slows down, we're going to see the light bend. So we can use Snell's law to mathematically predict how the light will refract. And so you have here a list of refraction indices. Each of these is basically comparing the effective speed of light through that medium with the actual speed of light in vacuum, which is why if you look here, we've got this equation that the index of refraction is equal to the speed of light divided by the actual velocity. So an index of refraction of 1 would be the same speed as vacuum. The larger this number gets, the more it's going to slow down. Does that make sense? Okay. So, yeah. So if you look here, like air, I told you the other day, air is essentially the same speed as vacuum. And you can see that here because the index is 1.000293, right? And so it's very close to 1. Where you start to see things happen are like water is 1.33. So water is going to cause light to refract more because it's going to slow down more as it goes through it. And what you see here is kind of common sense. When you know that the speed is effectively changing because of interactions with the medium, you would think that the gas would, or sorry, that the light would travel the fastest through gases and the slowest through solids because it has to be absorbed and re-emitted more times. Does that make sense? And we see that in the index here, right? So gases are generally quite low. Liquids generally around the 1.3 to 1.5-ish range. And then solids, you start to get much higher values, 1.5 to 2. Ice being an interesting one because of its structure, it actually more effectively travels than through water. So that is index of refraction. Questions about that? All right, so then we have what we call Snell's law. Snell's law will give you a mathematical way to predict how light will bend when it travels from one medium into another medium. So you can see the blue line there is showing the interface between the two media. And N1 would be the index of refraction of the first medium. The N2 is the index of refraction of the second medium. And there's a mathematical equation that you could use to show, if I know the two indices and I know the incident angle, then I can find the refracted angle. Now notice, those are both measured from normal. We're always measuring our angles from normal, okay? The reason we do that is because with a curved surface, the normal will still exist, whereas the plane will not. That's why we saw that with the law of reflection, and we see it with the law of refraction, that we always measure things from normal. So it's a simple equation, it's not hard to use. You know the indices, you plug in the numbers, no big deal, right? What we should see is that the larger the change, the more the light will bend. Cool? Okay. All right. Now there's an interesting phenomenon that can happen here, which is that at some point I can bend the light enough that I get what's called total internal reflection. So here's the deal. What really happens when light hits a boundary is some of the light goes through the interface and refracts. Some of the light bounces off the interface. That always happens. And the percentage that bounces back versus goes through depends on the two different indices and the angle that it's hitting at. Does that make any sense? Mm-hmm. This should make sense because you're probably familiar with glare on glass, right? That light is traveling through the glass, but there's also a glare on it, which is a reflection. And so this is something that you've probably already been aware of, but we haven't said out loud in a physics class, is that the light is coming through, some of it's bouncing off, and some of it's passing through. Yeah?
I have a question. You know how sometimes it's really hot and you it's really far out there and it looks like water or something?
Like the things?
Reflection?
So there's two things that happen there. One is the right angle to reflect the light. The other thing that happens is that as the heat disturbs the air is causing the light to reflect slightly, and as the heat is moving the air, then it kind of causes those wavy patterns. But yeah, that's actually, there are things that we see that are actually really complicated from a physics perspective. One of the most complicated things is actually, the rainbows that get formed when there's oil on top of water. Mm-hmm. You know what I'm talking about? Extremely mathematically complex to model, like super crazy. The basic phenomenon, not that complicated. Modeling it mathematically is a bear. That whole mirage thing, that's a similar really complicated to model. But it comes down to that phenomenon. So at some point, I should see that there's kind of a sweet spot angle where I don't get any refracted light at all. I could only get reflected light. And this is what fiber optics is built off of. So if you're familiar with fiber optics, you have a material that I can transmit data a lot faster if instead of traveling, putting signals through a wire, I just flash a light on one end. and then make sure that light reaches it, because then that signal travels at the speed of light, and I can send that signal incredibly quickly with these super fast flashes that computers can read but human eyes can't see. So total internal reflection, really important idea, because what I do is I design a cable so that no matter how the light is traveling through, it always reflects and stays inside that material. There's all sorts of issues about like signal getting bent and all that, but we're not here for that. So it turns out you can find that angle with this equation here, which is that the angle of total internal reflection, which we call the critical angle, is equal to the inverse sine of the ratio of the indices. Notice it's N2 over N1, so second medium over first medium. Simple equation to use, not that big of a deal. All right, this brings us to dispersion, so now we can talk about what's going on here. If we understand that light is going to bend as it passes through a medium, then we can understand that white light is actually made of like all the pure photons of light. And so as that light passes through, all of that light is going to bend, right? It's all going to go through this refraction process. And the short story here is that the light disperses by color. The reason for that is because when you look at all the different wavelengths here, they are going to bend a little bit differently, okay? All the light is actually going to travel through materials at slightly different speeds, okay? The reason for that comes down to, you know, how they're being absorbed and how they're being re-emitted, right? So again, I think this foundational understanding is important. If you understand that what's really happening as something goes through a material is it's absorbed and re-emitted, absorbed and re-emitted, absorbed and re-emitted, and then it pops out on the other side, right? Then it wouldn't be too much of a stretch to think that like, okay, so maybe purple light takes longer to be absorbed and re-emitted, right? It's actually the opposite. Maybe red light takes longer to be absorbed and re-emitted, and because of that, it's going to be slowed down more as it passes through the medium. So basically the idea is that all of these will reflect a little bit differently because they're all being absorbed and re-emitted a little bit differently, and so all of their speeds through the material will change a little bit differently. And if you can hit the perfect angle, then you will get all these different wavelengths of light to spread out. Like if the angle's not perfect, then they'll all be a little bit different, but they'll mainly stay together. If I can hit kind of the perfect angle, then they'll spread out where I can see the colors separate based on wavelength, and that's what creates the rainbow. Does that make sense? So the reason why rainbows exist at its core is because when light refracts, the different wavelengths all refract a little bit differently because of that whole speed change thing. And that causes the light to spread out. And so that white light comes in as white, being a mixture of all the different wavelengths, and then it gets broken up into all the various wavelengths. And how much it's broken up depends on how it's split up there. Now what's interesting about raindrops is there's actually two things going on. One is the dispersion as it hits the boundary, right? I've got the light that comes in, it's going to start breaking apart. But then the other thing that happens is you actually have a critical angle here for total internal reflection. And so when it hits the backside, it reflects and comes back down this way, and it continues to spread out more and more and more as it passes through this boundary until it comes out the other side, completely spread out and shining back at you. Does that make sense? So in the raindrop, you have splitting, reflecting internally, and then splitting again. And what we see then is the rainbow. Now, what's important here is that the angle that you're seeing is the critical factor. What I need to happen is for the angle the light is coming in at and the angle that I'm looking at to make a 42-degree angle. That's the magic number, 42 degrees. Okay? If the light is coming in at a 42-degree angle with my visual path, I will see a rainbow. This is why it's an arc. Because if I take that 42 degrees and I think about my whole visual path, then that will form a circle. So there are actually pictures of people flying in airplanes where they look down and they see a circular rainbow. because the only thing that stops you from seeing the full circle is that there's ground there, and so you don't see, there's nothing else to reflect the light, right? But that's why rainbows are rainbows, is because of this perfect sweet spot angle that we see here. So again, light comes in. This is actually the one that you want, the primary rainbow. The light comes in, it bounces off, and then it comes back and you can see it. Now here's the deal, is there's actually two sweet spot angles, it turns out. One at the top of the raindrop and then one at the bottom. So have you ever seen that video of the like Hawaiian dude or Polynesian dude, whatever he is, where he's like, oh my god, a double rainbow. You guys have seen that? Have you guys ever seen a double rainbow?
Yeah.
Okay, so double rainbows are a thing. The reason for that is there's actually two sweet spot angles. There's the one we normally see, which is this 42-degree guy. And there's also this one down here. Oh, sorry, not down here. Up here. There's this one up here where you see the same pattern, but because it's the water, but it's the light coming to the water at the bottom, you end up seeing the whole rainbow reversed. So the primary rainbow, the one we normally see, is going to follow the rainbow order, right? Red, orange, yellow, green, blue, violet, whatever. The secondary rainbow is going to be reversed. Red, orange, yellow, green, blue, violet. Does that make sense? And there's what's called the dark band in the middle. Not super important, but that's where like all the not visible spectrum is. It's there, we just can't see it. So that's why rainbows happen. Fun fact, now you should be able to go, be excited next time you see a rainbow that you understand why they happen. Questions? Yeah.
So what about like, I don't know.
Is my camera still on, by the way? Okay, yeah.
I don't know how to explain it, but like yesterday I was looking at my living room floor and I have like opened like a door like to my backyard that has a window and it was shining on something, but it was like on the ground there was a rainbow. So like how do you explain that there's like no water?
It's dispersion, but through the glass. So it's all that needs to happen for dispersion is for light to hit at kind of that sweet spot angle where you're going to be able to see that the light is refracting at slightly different angles. And so that happens with a lot of stuff. Yeah. It's also why lens, what do they call those? They're not lens flares. No, lens flares are white, right? Are lens flares rainbows? Okay. That's the same principle. So yeah, you'll see rainbows produced all the time because different things will do that. Like my brother-in-law got excited but also didn't understand what was happening because when the solar eclipse was happening, there were little rainbows that were formed as the light from the solar eclipse passed through his tree's leaves. It's the same principle, it's just that the light's bending at the perfect angle. Anyways. Questions? All right.